dive into today's talk. And so the idea here is for this to be sort of a tutorial in flavor. Okay, and so you may have heard about using logical relations as a proof technique. But if you've never seen it before, that's fine. This will be sort of a tutorial on using logical relations. And then furthermore, there's a certain flavor of logical relations called step index logical relations, which is the kind you typically need if you're doing a more full-fledged language, languages that have features that means the program might diverge, might go into an infinite loop, which is sort of most languages we deal with. So you'll need often step indexing. So we'll see how to do that. And I'm going to do a very, very simple application of logical relations to something that everyone should be familiar with, which is type safety. Okay. Now, I should say that using logical relations for type safety is overkill. Okay. So you don't just I've got other blog posts about like easy ways to prove type safety. If that's all you want to do, don't do logical relations. Just prove progress of iteration or whatever, and that's fine. Okay. But the idea here is that maybe what you really have in mind is you want to prove some more sophisticated theorem about program equivalence, or like I like proving stuff about what's called the gradual guarantee, where what happens when you change the amount of type information in the program, and what happens to the behavior as you do that. Or maybe you're interested in information flow security and you want to prove a non-interference theorem. These are all things that you could use logical relations to prove, and where other techniques maybe wouldn't be able to. Okay, but all of those applications are a lot more complicated, and so that's why I want to start out with sort of like something that we're all familiar with, just type safety. All right, so I should say that we're doing type safety for not just the simply type Lambda calculus, but STLC with general recursion, right, with fixed added on. The reason for that is that if it was just STLC, then we wouldn't need step indexing. Okay, just normal logical relations would be perfectly fine to handle that. Okay, but part of this is like, we want to get familiar with how to do deal with the step indexing. So that's why I'm adding in that to sort of force us to do that. And I didn't want to have the step indexing there for no reason. Okay, so that's why that's there. Okay, so here's kind of an outline of what we're going to talk about today. I'm just going to kind of briefly go over this definition of STL plus fix, and it's maybe slightly different from what you see like in TAPL. So that's why I kind of want to review that. And just review here's this theorem that we want to prove for type safety. Okay. And then I'm going to kind of go through the logical relations recipe. And one of the first things you do is you define a logical relation. So we'll sort of do a straw man version of that, and then see why that straw man doesn't work, and then why you need step indexing. And then we'll get into this logic that helps you do proofs about step index logical relations. So it's step index logic. It's kind of a modal logic or a temporal logic. Then we'll kind of spend a big chunk of the time actually diving into this proof of the fundamental language descriptor mean. So we review what you have to do. And at the very end, sort of have a fairly easy proof that this logical relation that you've created actually sort of gives you type safety. That's usually pretty straightforward because you define the logical relation to basically be type safety, to be what you want to prove. All right, so that's the outline of what we're going to do today. Any sort of questions? Okay. All right, so here's our little language of the STLC. We're going to have natural numbers in there, and also this the fixed point commutator here. The fixed point here. So u of n is going to be like, typically n is going to be like a lambda. It doesn't have to be, but we're going to force it to have function type. We're going to do the type system in a minute. So it's going to be a function here, and really it's like, oh, I want to turn this function into a recursive function. That's what that does. Okay. And then here's our reduction rules. And I should mention briefly that the way we're doing variables here is deploying variables. Okay. So the I there is for variables, and that's an index of a number, a natural number. Okay. And so substitution. Well, so you'll notice that like there aren't, like our lambda doesn't have an x, right? That's because it doesn't need it. It's the 0 number is going to correspond to referring to this lambda, right? And the same thing with our mu. You would normally have a variable there, but again, it's just grown. So you don't need an explicit variable. Oh, and then also like for this case, right? So this is for casing on natural numbers, and the L would be the natural number that you're casing on. M would be the branch for if L is 0, and then N is the branch if it's the successor. And if it's a successor, then you know in the N branch you get bound a variable to the thing inside the successor. So there's a bunch of variable binding. Maybe you'll see that in the typing rules too. Okay, now here's a little bit of an unusual way to go with how the mu works. Okay, so the idea here is that we're actually going to be kind of, mu of a value is actually just going to be a value in our world. Okay, so mu of v is a value. And it's a value that you see that it has to be a function type, which means we'll need to say what happens when we apply it. Okay, so the idea here is that at the moment of application, that's when we're going to sort of unfold the mu by one step, by substituting uv into itself. Okay. So sometimes people have, let's see, what's the alternative rule that maybe you'll see more often? Is you'll just have something that says mu of anything, goes to m with mu of m side. And this rule can sort of fire whenever you want it to, sort of non-deterministic in a manner. Okay. Whereas this is, here we're saying, actually, you know what that reminds me of? Actually, I think I forgot. One of the frames says you can evaluate inside of u to get a value. Or maybe
you need that.
Yeah. It's on this account.
Numbering from inside out, correct?
Yes. Okay, the other little thing to notice here is that we have these frames, which are these thin frames, and then there's this rule that says, like, each one of them has a box where the hole is. Plug this notation is for plugging m into the box. And then this rule is like your typical sort of like converse rule that says, okay, you can step one of the sub-expressions and the whole thing steps. Right? Yeah. It's kind of nice to just have one rule like this instead of having a whole bunch of sort of different versions of F. Okay. Here's the type system. So the main thing. Well, actually, there's a couple kind of unusual things here. One is that there's sort of like a separate type system for values, and then another type system for expressions or terms. Okay, and there's sort of this one rule that says, oh, if you're a value, then you're also a well-typed value, then you're also a well-typed term. Right, and then, so actually, I guess what I'm saying here, actually, I think back now, we didn't need the frame for mu n. Really, you basically have to type in a value to begin with.
That's in the syntax.
It's in the type system. So I could have put it in the syntax too. It turns out I didn't, but this is almost the same thing.
So basically, the n can come from a lambda or something, right?
Yeah. So you could have several mu's.
A lambda inside it.
In a row, you could, and then a lambda. But the usual thing is a mu and a lambda.
Yeah.
Okay. Right, so there's the types, and yeah, explicitly the views have to have function type. The thing inside has to have function type, and the zero variable here is has to have function type. Oh, and I'm a little bit schizophrenic about putting things to the, adding to the consing to the environment on the right or the left. I'm sorry. And then I meant to switch them all to be to this way on the left. Okay. It's more traditional to do it this way, but okay. All right. So we want to prove type safety, and the typical way you prove type safety is you'd prove like a progress. You'd sort of directly prove progress and preservation, and then you get your type safety out of it. Now, to do this by logical relations, we're gonna define these logical relations, and typically what you do is you're like, oh, what do I need to prove? I'm going to take that thing I'm proving and sort of jam it into this logical relation in terms of how I define the logical relation. And there's some sort of, you have a lot of choice about how you do that, right? And what people typically do actually is they take the actual final theorem they want to prove, and they use this to guide the definition of their logical relation. But today I'm going to do a slightly different thing, which is I'm actually going to take these two lemmas, and I'm going to use these two lemmas to sort of guide how we define the logical relation. And then they'll be sort of like a sort of simple step at the very end to sort of prove type safety. Okay. So the logical relations will give us progress and preservation. So we'll think about it. And then we'll do induction on reduction steps at the very end. And part of this is to show that there's lots of choices. Also, part of why I'm doing it this way, not this way, is that it's going to be a little bit easier to deal with our step index logic. We sort of only have to deal with like one step at a time. Okay. All right, so I want to do a little bit of an aside about the ground variables. Okay, so our ground variables, like I said, are just numbers, 0, 1, 2, 3, and so on. So we're going to be working with substitutions a fair bit. So a substitution at a high level is just a mapping of variables to terms. Because our variables are numbers, we can think of a substitution we represent just as a sequence of terms. Okay? And that's kind of helpful because now we know how to think about sequences or cons lists, right? And con stuff on the front. We do lookups and stuff in sequences. And then when you can apply a substitution to a term, right? So this is sometimes called like parallel substitution, or what's the other name for it? Yeah, simultaneous substitution. Thank you. Right. And the basic idea is you dive down until you get to a variable, and then you just look up the ith variable of the substitution. The one little thing to note here is that when you get to a place where there's a binder, like let's say you get to a lambda and you want to go underneath the lambda, then you actually have to do some massaging to your substitution to handle the fact that you're going under a binder. Okay, and this is like because you got the ground variables, right? So the main thing when you go under the binder is that you don't want your substitution to do anything to the bound variable. Right? That bound variable is variable number 0. You don't want your substitution to do anything to 0. So this substitution, this x function, is going to map 0 to 0. So that's what that's doing right there, 0 to 0. The other thing that you need to worry about is, well, your substitution before it went underneath this lambda, it had a bunch of the ground variables, a bunch of numbers that were referring to lambdas somewhere up above. And now you're going underneath this lambda, and so all those variables are getting a little bit further away. Okay? You're now like one hop further away. So you need to add one to all those variables. And that's what this up arrow is doing. It's adding one to all the variables that are inside those terms. Okay, so that's what the x function does. And you can see you can use it there, you can use it when we go under the new, you can use it on the end part of the case, because those are all the places where we're going to find it. So this is kind of the what I would call the Conor McBride sort of style of doing de Bruijn indices, of having them all based on this simultaneous substitution. If you go and look at Capel and read about de Bruijn indices, they'll show you how to sort of substitute one thing at a time. And I find that harder to deal with in a proof assistant and doing the parallel substitution thing. So there's so many different ways of doing variables. You know, there's the locally nameless, there's the higher order abstract syntax, there's the parametric higher order abstract syntax, there's all these different ones. I've sort of kind of settled on this as like as the least bad for me. The nice thing about it, I oftentimes can sort of forget about variables after doing this and not have to think about them too much, which is yay. Okay, so that's substitution. Let's dive into the logical relations. Okay, so here's the recipe for doing the logical relations proof technique. Okay, so you're going to define two functions that generalize the theorem that you'd like to prove. Okay, one maps types to a predicate on closed values. That's this fancy function. And then there's this fancy E function that maps types to a predicate on closed terms. Okay, so the type of V applied to A applied to V, that's just going to be a Boolean, right? Or, you know, if you're an AGA, it's going to be set or plot or something, or similar in AGA. Okay, so once you've got those, and defining these is, you want to be, this is a sort of an important point. Doing that carefully, doing it quite is important. And actually, that's why you might actually want to do this last bullet item right after doing that first one. Like I have it down here, but you might want to double check you've got this right by going ahead and proving that your definition of CurlyE should sort of immediately imply the theorem that you want. Right? So this should be easy to prove. If this turns out to be hard or impossible, then you want to kind of go back to the drawing board and fix up your definition of fancy E. And the next thing you do, and this is fairly simple, you just do these definitions basically, which is you want to extend V and E to handle open terms. Okay? And right, so here it's basically these two relations with this auxiliary thing, which is like, and this is meant to sort of look a little bit like a typing derivation, but this is more like saying you're semantically, maybe I should say one thing. I tend to like using a certain slogan for this V and E. And the slogan, because these are going to be actually semantic things that talk about the actual behavior of the program, okay? So I like to think of these as being, expressing what it means to be well-behaved for whatever theorem, whatever that means according to the theorem you care about. You know, you kind of have this notion of what does it mean for them to be well-behaved? That's what you're defining with V and E. It's well-behaved terms, well-behaved values. Okay, but these are closed. Okay, so now here what we're doing is we're saying, okay, we're going to quantify over any substitution, as long as that substitution is mapping variables to well-behaved values. Okay, so give me any substitution that maps to well-behaved values. Go ahead and apply that substitution and then to some, my term M, and I'll have a well-behaved term. Okay, so that's what this means, similarly for values. So that's how we go to open terms. As in open terms, now we have lots of free variables in those terms, and the idea is, well, we can close them by applying the substitution. We just have to say, oh, that substitution needs to be one that maps variables to well-behaved values. Of course, this recipe, this is a very generic recipe. It's like, well, what theorem are you trying to prove? And then that's going to reflect the E and the V. Okay, so we'll get into an example of that in a second.
So the theorem is something like, the theorem you want is for every term m of type A, blah, 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 right? Like the theorem
Yes.
is universally quantified over well-typed terms.
Yes, this is only going to be for, statically typed language in some sense, and only for well-typed terms, because, at the end of the day, we're gonna take this. So we have this fundamental. So the next step is this fundamental lemma, which says that if you have a well-typed term, then you have a well-behaved term, semantically good, right? And so this is going to be our starting point. So, to prove, whatever theorem we want, it's going to have a premise of you're well-typed. That's going to then give you that, which is sort of equivalent to this, and that'll get you to the final whatever thing you want, whether that's non-interference or type safety or whatever. Okay, so what we're going to do for the rest of the time here is basically follow this recipe for type safety. Okay, so our goal will be type safety here. Okay. All right. So here's a first attempt at type safety. Let's start with the CurlyE. Okay. And so what I've written down here for the definition of CurlyE is essentially progress and preservation. Okay. Now let's start with the progress part. Now normally progress would say either m is a value or you take a step. The taking a step part is exactly that, right? But instead of saying they're just a value, this is the generalization part that I was referring to earlier. I'm going to generalize being a value to not just being a value, but to be a well-behaved value. Okay? So I'm using the CurlyE here instead of just saying that it's a value. Okay? All right, so then what does it mean to be a well-behaved value? Well, for some of these, it's going to be pretty trivial. So, like if you're 0, oh, and by the way, we're doing this like by type, okay? So like, if you're a well-behaved natural number, yeah, 0 is a well-behaved natural number. Okay? So the successor of something is a well-behaved natural number if, well, that something V is a well-behaved natural number. You have a question?
Well, it's more about the E. There's recursion in this definition.
Oh, yes, I forgot to do the preservation part. Yeah, so thank you. I jumped ahead. So we talked about the progress part. The preservation part, you could say, like normally you say, oh, you can take a step and then you'll be well-typed after one step. But again, we want to generalize that here to now be a sort of a semantic thing. And to say, oh, after one step, you're still a well-behaved term.
But the right-hand side uses E of A.
Yes.
So
Yes, this is
what
what
does it mean by that, right?
So this is a recursive predicate. And we have to now worry about whether it's a well-defined recursive predicate or not.
Yeah, it's closer. Are we taking the leaf or the...
Yeah, so hold that thought, hold this thought.
So
this is
that's not defined yet, right? I don't know what that means.
That's fine, yes. And in fact it is because this is the straw man. And so this is actually a bogus, recursive predicate.
Fine.
And so,
Okay, so might as well just be bogus all this. Fine.
yes.
Same thing.
And then part of I'm pointing out part of the red thing is part of why it's bogus.
But that's also fine.
Yeah. Okay. Yeah, I should have had that note too, but I didn't. Anyway. Okay, now let's talk about, well, what does it mean to be a well-behaved lambda? Okay, this gets interesting. Okay, this is where good old logical relations, forget about step indexing, this is why you need sort of logical relations, is that normally when you get to the point of doing an application, in one of these proofs you get stuck, and that's where you actually decide, oh, I need logical relations, because what's this going to do? This is going to be really powerful here. It's going to say, okay, I'm a well-behaved lambda if give me any well-behaved argument, W, and the body of this function is going to be well behaved. Okay? So here we've packaged up sort of everything you need to know about this lambda so that later on when we apply it, we'll know that we have a well-behaved lambda, and that's going to give us a well-behaved body. And we're going to be able to keep running the body, okay, and prove what we need to prove about it. Okay? So this kind of thing, you're going to see this over and over again whenever you're doing logical relation, defining a logical relation. For the lambda case, you're going to quantify over all arguments. And then you're going to say that you've got a good body. Okay? And then for sort of similarly for mu here, for recursion, what this is saying is, okay, if I've got a well-behaved mu, that means I can unfold it once, and that's still well-behaved. Okay? And then all the other cases are false. Okay? Now, one of the reasons why this recursive definition is bogus is that, well, typically with logical relations, they're well-founded because of this first argument. You're doing recursion on the types. Like, let's say we were just doing STLC. We'd be doing recursion on the types. And if you ignore this line here, you'll notice that when we do recursion, the types are getting smaller. Okay, and normally that would be enough to, and maybe here we would, instead of doing it this way, we might sort of multi-step and not have to use that recursively at all there. And so then you get a well-defined relation that way. But here we've added mu, and so here it's like, oh, this still has the same type. This is not getting smaller, so this, this definition is bogus. Right? And so this is where it's like, oh, why do we need step indexing? It's so that we can do these recursive definitions and have them actually be real recursive definitions, okay, and not true bogus ones.
So not only is the type not shrinking, the term is also not shrinking, right? Because
Yeah.
where the type does not
Could be
shrink.
getting bigger.
Yeah.
The term's not shrinking is not the problem, right? Like,
Yes.
on the line.
The relations are no longer just predicates. They're now step index predicates. So in other words, they're functions from natural numbers to booleans. Okay, and this is sort of a very, very rough analogy, but you know how like when you turn something into a monad, you're now like threading stuff through? It's a little bit like that. We're now threading through this step index, this natural number is being threaded through everywhere, okay? And I'll show you in a little bit sort of a sketch at how you define these operators. That's all going to be on the next page. But the main thing to realize here is that we've got this triangle, okay? Now, and we've sprinkled the triangle in front of every recursive call, okay? So the triangle means later, okay? That's our temporal operator. It means sort of one step in the future, okay? And now, these definitions are, the well-foundedness of them is going to be based just on the natural number getting smaller, okay? And because we've put a later up in front of all of our recursive calls, now all those recursive calls are happening at a smaller integer, okay? And what's a little bit weird about the time here is time is counting down. Okay, it's the way to think about it. So like you're counting down to 0.
Can you actually type this into Lambda?
Yes.
Wow.
So, well, not exactly like this. So I've sort of previewed this up. So maybe once I should have maybe done this in the introduction. So all of this is based on an AGDA development that I've done. Okay, so I've developed a step index logic in AGDA as like a library. And then as like a case study, I did this proof on top of that library, okay? And here I'm glossing over a few of the details. So here I've sort of made it look as if E and V are functions that maybe you type into AGDA as functions. But that's actually not how it works. works. Instead, the step index logic has an operator for a recursive predicate definition. Okay, and then there's a way of saying, oh, I want to make a recursive call to the, the mu thing that's in the scope, which is my recursive predicate. And so it turns out you're not actually using Agda's recursion at all. You're using sort of the library's notion of recursion. Okay, but sort of concept, it's morally equivalent to what I've got.
Why doesn't it work to just type this in?
So it's basically two things. One is that this is it's really strong induction that's going on here because of how I'm defining the triangle. There's sort of technical. You could do it with more regular induction, but it turns out to be easier this way. And then the other thing is that Agda can't sort of see through all the library layer to know that things are getting smaller. Like, it can't see, basically there's all these library combinators, all these logical operators, and they're doing the arithmetic, and it can't see through that to understand the termination.
So like if I inline all the circle stuff from your library into this slide, even then you're saying I don't know what's
Then because, well here, then there's hope of making that work with a slightly different way of doing it than what I've done. So yeah, but I think that's a good intuition that, there's hope that if you inline everything, then Agda could figure it out. So let's this is like the gist of how these operators are defined, okay? So all these operators now, these step index logic formulas aren't just Boolean type things, they're in some natural number to Boolean, right? So for some of these things, that's pretty trivial. So like for true circle and false circle, they just ignore the step index. Okay, so true is true, false is false. For things like and or and for all, you basically just propagate the steps inside. Okay, so that's no big deal. The main thing is here is how you define your later operator. And the way I like to do it, and now I'm remembering why, is good. I like to say, for all j smaller than k, phi of j is true. Okay, and so this is what I meant by, this is sort of like akin to strong induction here. And so like Agda won't right off the bat understand those recursive calls that are using j. It won't understand right away that those are smaller, because it only understands really normal induction of like -1, right? Instead of this. However, you can do strong induction or strong recursion in Agda, and then you'd be okay.
Should there be a circle on for all on the left-hand side?
Yes, there should. Okay, now why do I like doing it this way instead of like, what I could do is instead say like, this is actually a fairly recent sort of insight that I've sort of had. So you could also be like, okay, what's the meaning of that applied to successor of k? Could be then, I guess it would just be phi of k. If you do that, then you also need to define that for 0, right? And that's part of the problem, is you then 0, and typically what people do here is that they just say true, okay? Which is a little bit weird. But the main problem is now we have these two cases, and there's like, Agda won't like automatically reason about cases, and so the rewriting that can happen automatically using definition of equality gets sort of like stuck all the time, and then you're like constantly doing cases. Whereas here, there's no cases, and so it's just great. Like definition of equality is just unfolding this and doing lots of stuff, and things work great. So that's why I like doing that better. Okay, cool. So this is just a gist of this. The actual library is way, way, way more complicated. Mostly to define, it's like thousand lines of Agda. Mostly because I have to define that my own recursion operator, and then prove that that thing behaves the way it's supposed to, which requires proving these fixed point theorems, and that gets exciting. And it was cool, like I liked doing it based off of, there's an early paper by Appel and McAllister, and I basically just followed their theorems, even though their theorems were not about doing the logic, they were just doing one of these logical relations proofs, but thanks to sort of a Curry Howard ice I was able to take their proofs about types and switch it over to being proofs about logic formulas. But anyway, so I was able to take their lemmas and type them into Agda and get a fixed point there. So that was cool. All right, but this is the gist of it. Okay. Then we're going to want like a proof theory for this logic. We're going to want lots of like proof rules that we can then use. So we don't have to reason about this explicitly. We want to just be able to do our normal sort of logic thinking. Okay. And so here's sort of our turnstile for that we're going to be using in our proofs. And but this is sort of like a light embedding approach. So the way we're actually going to define this is sort of semantically that it literally means like, okay, all the premises for any step index k, if all the premises are true at k, then phi k needs to be true. Okay. So this basically means like, okay, I have a bunch of premises and a conclusion, and this will hold when for all step indexes the premises imply the conclusion. Okay. All right, then what we can then go and do is like as derived lemmas, go prove rules like this. Okay, so these are all things that I've proved in the library. They're rules that I've proved in the library, which you can then use. Okay, and I'm not showing all the normal rules that you have for a logic, like there's modus ponens and all those ones that you know of. Okay, and those all work as you'd expect. Here's the rules for the later operator, because maybe you haven't seen them in modal logic, and so whether how these rules work. Now, one thing that's interesting about this modal logic is the way it's set up is that things that are true now are always true in the future as well. Okay, I think that's not all. Is that always? Temporal logics don't always do that, right?
No, so that's why this first rule here is kind of surprising.
Right. Yeah. So this is a very special kind of temporal logic, and basically, this is, by the way, this logic is descended from this LSLR logic from Amal, Berkedal, Dreyer. They do that too. And this is,
Isn't that like an invariant you have to maintain for
Yes.
all fees?
yes.
Okay, so fees.
So maybe one way to think about this is that logical relations, if you're building on this logic, the kind of properties you care about are program invariants.
Sure, so like I think maybe it's on the previous slide where you said N to B, right? Like where you say what a proposition is nowadays is N to B, like upper left corner, right?
Right.
And it sounds like that's hiding, like maybe it's not all N to B. It sounds like it's not like we can just, like that rule you showed in the next slide is not true for all phi that are N to B, right?
Right.
It's only true for whatever monotonic, I don't know.
Yes, yes.
N to B.
So one of the things that, this is going to require that all the formulas are monotonic.
Okay.
And in fact, one of the nice things about the library is that the library sort of builds in the fact that these are monotonic as like into the smart constructors.
Okay.
So the smart constructors all carry proofs of monotonicity, and sort of I've done the work for that. Whereas if you were doing this by hand and not using the library, then you would have to prove by hand that your V and your E are monotonic, which is boring and a pain in the neck. So yeah, good. Yeah.
And that it comes for free because we write our propositions in effectively this circle of DSL.
Yes.
Which
DSL, the circle DSL is
which
giving
prevents us from even looking at K and thus writing functions that do the wrong thing.
Okay. Is not allowed.
Yeah.
Right, yes.
N to B function.
Yeah. Well, one thing I should mention too, I'm sort of hiding it here, but you'll see that there's places like this where I talk about M to M prime here. That's not in the logic. That's not in the DSL. There's an escape hatch that lets you say, oh, I want to sort of talk about any AGDA thing. And the skape hatch works in a pretty simple way. It's like, give me any AGDA proposition, and I'll inject it into the logic by ignoring the step index. So,
It's like a unit pure of the mode.
yeah. Okay, cool. Okay, so let's talk a little bit. So we talked about this first rule. It says if something's true now, that's going to be true in the future. And this is basically, this is using the monotonicity, right? This is like, oh, the logic has been built so it's monotonic, and now we get to use that fact here. This is a pretty standard property of a world logic, which is you can distribute through like implication. And I did ... because you can distribute through just about everything. And, or, for all exists. You can distribute through it. And then this one, this is actually sort of a simple derived rule, but it's kind of handy. Which is, let's say you know that like phi implies psi. But you don't know phi, you know later phi. Well, then you can derive later psi from that. If you want, you can think about like how you may use some of these other rules to prove that one. But I end up using that one. You need to use that one there.
It's like cut elimination. That's like cut.
Yeah. This is like it's like a cut elimination with a twist. Later. Okay, then here's something that's kind of interesting and important. This is load induction. We're going to use this a bunch of times. Okay. And load induction says that, okay, let's say you're trying to prove phi. Then, on your way to doing that, you can assume later phi. Okay, so this is like, for free, you get to be like, oh, I can whenever I'm trying to prove something, I can assume later of that thing. Okay, and this, at first you might look, it's got a funny name, with some umlauts, it's maybe a little scary. I found it a little scary. Ooh, who's Low? And then I read about Low, he's a logician, and he did this stuff that was all very fancy and complicated. So what is this? This is really just strong induction right here. That's all this is, okay? Because, later, remember that says, oh, for all smaller j, okay? So this is like your typical, induction case for strong induction. And then that's all you need, right, in strong. You just have that one thing to prove. You don't have a base case to deal with in strong induction. So this is just, and the way actually this is proved in the library is literally just using strong induction to prove that. Okay, so the low induction will be pretty good. Okay, looking at my time. I think I've got 15 minutes. All right. I think I'm going to skip over some stuff. Okay, now the next part of the recipe is that we need to extend V and E to open terms. So I'm going to do this just slightly differently than the way I showed it before with the strongman, or on that recipe slide. Is that this, this is our gamma here, which is going to be a sequence of types. Okay, and then what we're going to put over here is not just a true or false, but it's going to be a list of these, applying, V to a term.
And these are well-behavednesses.
And you can tell, these are always still waiting for a step index. So it's a list of mapped rules. Okay. And then, then how am I going to define it? Well, this actually, the reason why I'm doing it that way is that it works nicely with my turnstile. Remember, the turnstile is expecting a list of these things. And so that's exactly what we're getting.
So this is kind of like a step index logical relations recipe, step 2.
Yes. Yeah. So here I'm, tweaking the recipe a little bit for step index. Okay. All right. So then the next thing is we need to prove the fundamental lemma, which is basically saying like, okay, if something's well typed, then it needs to be actually semantically well behaved. Okay, this is where sort of all the work happens. And the overall proof structure is pretty straightforward. You just do mutual induction on these two typing derivations, okay? And then each case of that proof, well, traditionally you define a separate lemma for each of those cases, and they're called compatibility lemmas. Okay, so if you hear a compatibility lemma, people are talking about just the cases of that proof. Okay. All right, let's start looking at some of these compatibility lemmas. Some of them are super easy, some of them are harder. So like this one is super easy. So we're trying to prove that 0 is sort of well-behaved. If we unfold this definition, remember that means like, oh, for any substitution, blah, blah, blah. Right, so let's let S be that substitution, and then we need to show that, the V here, the fancy V with the substitution applied to 0. Of course, that substitution applied to 0 is just 0, okay? And then the meaning curly V of 0, if you remember that definition, it was just true. And so we just need to prove true, which of course is, the trivial library provides that. It's called TT circle is the rule for that, just imitating that, right? Okay, so that one's easy. This one's pretty easy too. So this is if you've got successor of a value. Okay, the reason why I'm showing this is that we get a premise here because when we're doing that mutual induction, we get our induction hypothesis, right? And so this is going to be the induction hypothesis for this case. Okay, so now we've got premises, which are essentially our induction hypotheses. Okay, so again, we're quantifying over any substitution, and then we need to prove this. The substitution slides inside, and then the meaning of curly V on successor of something says, oh, that's true as long as you have curly V on the thing inside the successor. Okay, so we need to prove that. But we can just instantiate this to sigma and hammer it out. So that one was super easy too.
So this premise is something you get from, first of all, like you have to do inversion on the typing derivation, right? Like this compatibility, I don't think compatibility, we're trying to prove like part 1.
Right, we're proving part 1 here. And so we're doing induction on this.
Yeah.
And so we'll get our conclusions for the sub derivations. And so that's where that's coming from.
And this is induction on like the step index and the type and
No. This is induction on the typing derivation.
Okay.
Right. So we're doing
Right.
right. So when you're looking at a typing derivation. Like that was way back at the very beginning. Let's power back to there, since it was so far back. But we're doing induction on this thing, and so it's that case that we're concerned about. So we're getting the induction hypothesis for that, and so that one with the double thing models symbol. That's the conclusion of that induction hypothesis, right, that we get to use. So that's where that comes from. Here. Okay. Good. All right. So those were simple, but it's also illustrative. Okay, this is an interesting case, and this is where. For the case for Lambda is like half of the story about how logical relations typically work, and then the other half is going to be application. And what's nice about the Lambda case is basically what we need to prove, we mostly just get by the induction hypothesis. Okay? So our induction hypothesis is here, which is saying that the body is semantically well behaved. Okay? In a sort of a slightly bigger environment here, right? We have a parameter from our lambda of type A, right? But then we need to prove that this thing is well behaved. Well, what is that? So we let S be any substitution. And then here's the definition of curly V for lambda, right? right? So we remember that we need to show that if we're given an argument, oh, and then remember, because we're doing step indexing, we put laters everywhere. There's recursion, so we put laters there and laters there. So we're saying, okay, if we're given a well-behaved argument, then the body is well-behaved. Okay. And notice that we had to apply a substitution to our lambda. When you move that substitution inside the lambda, it gets x'd, it gets extended, right? And then we're, and that with the argument substituted in is well-behaved. So that's what we need to. We need to prove this implication. Okay. So we've got this for all and an implication. So we can let W being any old value and assume that it's well-behaved later. Okay. Now we have this premise to use. Okay. So from that premise, we can plug in the substitution that we're going to plug in is sigma with W added on to the front. Okay. And so that premise is going to tell us that N with that substitution is well behaved at type B. Okay, and I've expanded this out a little bit. Now here we're going to use one of those proof rules for the sort of one that looks a little bit like cut elimination. Okay, we've got we know that later of VW is true. Okay, which is like that premise. And so what we can derive then using that rule is later of this conclusion. Right, so now we have later of that. Okay. So now this is almost what we need to prove up here. Okay, but we've just got there's some funny business going on with substitutions. Okay, so it turns out that those are equivalent. Okay, and this is a pretty standard lemma about substitutions. That's a pain in the neck to prove. But like if you use my abstract binding tree library, then it's done once and for all, and you don't have to do it too. It's kind of cool. All right, but on paper it's kind of easy to understand what it's doing. So what is x of n and then with substitution w? Well, if you remember, so x of something maps 0 to 0, and this substitution says put that in for 0. So there's our w. Okay. The other thing that's going on is this x is going to raise everything by 1, right? So that's the raising. But then the bracket substitution is then going to lower everything else by 1. Okay. So you get all these ups and downs canceling out, and so this just ends up being, the sequence with w at the front and then s for the rest, which is what we have down here, whereas the other side is what we have up there. So cool, we're good. So, yeah, so the kind of the main takeaway from this is that for the lambda case, most of what we need came from the induction hypothesis. And then there's some, technical stuff. Okay. Let's skip, no. Should we do this one?
I don't have to talk next week.
What's that?
I don't know. I forget.
We could just keep going next week, is what you're suggesting? That's maybe not a bad idea. I don't know.
Actually, we have 15 extra minutes because I reserved the room until like 12:30. So
Kind of depends on how what we want to do. We can, I'll go for a
If I
5
pick one compatibility, if you do this, nobody will do applications.
Yeah, so that was my thing, is like, I could probably do one more slide. I could do application.
But don't we still have to get to the fundamental lemma?
These are all the subcases.
Oh, okay.
So these are all So once we finish all these compatibility lemmas, we're done with the fundamental lemma.
Let's just do this slide.
Yeah, okay, we'll just do this slide. So this is the one from you. Okay, and one of the interesting things about this slide is that we're going to end up using lobe induction. Okay, so that's exciting. Okay, so here's our induction hypothesis, and then here's what we want to prove, that mu is well behaved. So we're gonna start out by saying, okay, let S be an old substitution. And so then what we need to prove then, unwinding that definition, is with the substitution thrown in, is we need to prove curly V of this mu, but now it's with this extended substitution in there, okay? And we're going to prove this by lobe induction, which means that we get to, this thing that we're trying to prove, we get to assume later of the exact same thing. Okay, so that's our induction hypothesis for the lobe induction. Okay? All right, now let's look at our premise up here. Okay, we can instantiate that on this substitution here. Okay, which is the substitution with, now we want to substitute ourselves into the mu. So for the zero variable, so that's what that's for. Okay, so we're instantiating this with that substitution. Okay, which gives us that V with this substitution is well behaved. Okay. Okay. I could have made this a little simpler, but here what I'm doing is if you peel off part of this, that's going to be a curly V about A arrow B as a premise, and here I'm moving that over now as, like as in function, implication introduction, moving it over here to that side. And then, actually, I really didn't need to do this line.
Because you're going to use IH, right?
Yeah, you're going to use IH, and then this is going to match up with part of that, and we're going to be able to do that, use that same sort of cut elimination style rule to give us that. Okay. And then this is equivalent to our goal. That's not completely obvious that it's equivalent. Again, we have some, a substitution that looks like that versus something with an X in it. So it's the same exact reason we did for the last slide to show that those are really equivalent.
And you're also using the definition of curly V for mu.
That's right, yes. To get that as well, right. That as well, yes. So, when you see lobe induction showing up, it's like, oh, this is where the step indexing is doing its work, and it's showing up where we have this view, where we have a recursion kind of thing showing up. All right, so I guess we're out of time.
If we click next a couple times?
Let's see, there's 1, 2, 3. There's three more stuff about compatibility levels, and then actually maybe if you want to go another 5 minutes, we can sort of tie the knot here.
Yeah, I would like that.
Yeah. So because at the end of the day, what we want is this final type safety theorem, right? And so to sort of put the icing on the cake, so to speak, we need to prove this lemma, okay, which is basically saying, because the CurlyE gave us progress in preservation, right? Sort of one-step preservation. Okay. What this lemma does is says, okay, let's deal with multi-step. Okay. It says if I multi-step from M to N, then and if I was a well-behaved term, then so is N after all those steps. And this is a super easy proof. I can just do it by induction on reduction sequence. And I just keep using the preservation part of E's definition over and over again.
And each time you use that, you're, incrementing or decrementing the step index once, right? So
yeah,
basically the step index is counting how long your sequence.
Yeah, you have to sort of count this sequence ahead of time so that you pick a step index that's big enough. And actually, that's an important point. This is where, this moment here is the first moment in time when the logical notion of time got actually connected to a step of reduction. Okay, because the logic doesn't really care about what time means. It's like, okay, it has a notion of time, but it's not connected to anything. Whereas here, all of a sudden, we've just so happened to connect each sort of later operator to sort of one reduction step. Okay, and then once we have that lemma, it's fairly straightforward to prove type safety. Okay, so we've got that m is well typed, and we know that m goes to some term n, and we want to know that either n is either a value or it can take another step. Okay. So how can we prove this? Well, from the fact that it's well typed, we can use the fundamental lemma to obtain that it's well behaved. And then I can then feed that into the multi-step preservation. So now I know that the n is well behaved. And then the definition of E, right? E means progress and preservation. So I can just take the progress part of E. And that's going to tell me that either n is a value or it can take a step. Okay. And the progress part actually had more than just that it was a value, syntactic value. It had that it was like, oh, it's a well-behaved value. But this is implied by that. So that's it. So that's type safety via. That's like the hard. I had like a bunch of blog posts about like what's the easiest way to do type safety proofs, and like 3 lemmas or 2 lemmas or whatever. This is like a really hard way to do it. Okay. Perhaps the hardest way to do type safety. But hopefully this has given you a little flavor of how you do how you use logical relations. And the good thing about logical relations is you've got some more complicated things you want to prove. They'll be able to handle that without, with more complications than this, but the same recipe will still work.
I think the hardest way would be to give a denotational model for this using scape domains and then show adequacy, and then that has type safety as a consequence.
Yes.
I think that's a Twitter.
So I was looking forward to this, and somehow somebody sent an email with calendar invites that had central time.
The calendar invites that I added had the right.
It shows I'm starting something now. I was so confused. But is it recorded?
It is recorded.
Can I
Yeah,
access
it's
it?
recorded.
Yes.
Okay, so I was looking forward to this. By the way, if I never get other slides, I might kind of ask you a question.
Sure. Yeah. Absolutely. Yeah. And unfortunately, Carlo couldn't make it either. So
I had full intention of making it, and I was here, actually, it's in my office.
Yeah.
I had a student come and walk. It's like, oh, I have to go now.
So hopefully, so I've spent a lot of time reading like papers by Derek Pryor and Mall about doing logical relations, and they're pretty hard reading. And so hopefully this talk has helped give you a little bit of a foothold or a toe into.
I'll teach it in 522, and I'll be forced to know it.
Yes. Yeah, and there is an ag, I'll repeat it, there's an ag development behind all of this.
Yeah, but
Yeah.
what does it mean for size type, something like this? Or no?
No, it's vanilla ag. Do I enable, yeah, it's vanilla ag. One interesting question is whether, so I went and sort of built this DSL. It's the step index logic. So this is implemented as a domain-specific language in AGDA. I could have instead used guarded cubicle AGDA instead of sort of rolling my own DSL. And so actually I kind of wanted to touch base with Carlo about like what his thoughts are and maybe learn about how to go about doing that. Trying this out with guarded
So it's because it's a high reductive type and has a query, so that's why we need cubicles.
Well, so in some sense, the main point of this logic is to let you do recursive predicate definitions in situations where doing those recursive definitions in AGDA would normally fall down, either because of negative recursion, or, here I'll try to do it as a function, but then you've got places where it doesn't get smaller and stuff like that. And so here with this DSL, you basically can do any kind of recursion you want. You just have to sprinkle a later operator in front of every, which in the guarded cubicle agate terminology is that you're guarding the recursion. And then where you put the guard sort of then controls like what your induction rule is for those things. And that actually corresponds to what happens with load induction.
And you use the cubicle for time? Or what do you use the cubicle?
Well, the guard is guarded cubicle. I don't know why guarded is on top of cubicle.
Yeah,
There's the guarded part that we care about.
Okay, yeah.
But there's no guarded without cubicle. At least I'm not that I know of. So, and I'm sure there's reasons for why they built it on top of cubicle. Carlo might know. I mean, I know he didn't build that one in particular, but this is like his sort of neck of the woods.
Is this similar to size types? I don't really understand size types.
Yeah, I don't know size types either. I mean,
Yeah, but size types are last I heard they stayed everybody.
they're still buggy.
Last I heard.
Yeah, okay. Yeah, so the downside of this way, well, for one thing is that if the actual agda of how you do this, there's a fair bit of syntactic noise of using this DSL. Right? This DSL is kind of a pain to use, okay? Like, especially when you get into doing the proofs, like when you're doing these proofs here, if you're using sort of like these DSL lemma or rules all over the place, and those are harder to use than normal active, function application kinds of thing, or lemma invocation, because like if you're doing a lemma invocation in active, it'll like let you implicitly instantiate for alls and it's doing all kinds of nice things for you automatically, and none of that happens automatically here. So you're like nitty gritty, like instantiating for alls explicitly and all this stuff, which is a pain. So it sort of like blows up your proof size by like a factor of 2 or so. And so, like maybe with guarded cubicle agda, you wouldn't be paying that price. So that would be cool if, And so I mean, part of why I did it this way was, guard cubicles are still sort of experimental. So if you just kind of want to have something that you can rely on today, this is that. And also, I got to learn a lot about fixed point theorems, step indexing.